Right now, somewhere in Memphis, Tennessee, there is a building the size of several football fields. Inside it, 100,000 NVIDIA H100 graphics cards are buzzing. This is the Colossus, Elon Musk's 11 supercomputer. His name was not exactly like that. This is something huge, something that crushes everything around you. But the Colossus has a fundamental problem. It burns in a figurative sense. Each of the 100,000 video cards inside this building consumes 7 watts of power. Multiply 7 by 100,000 and you get 70 megawatts for only one video card. And there are also server boards, feeding blocks, cooling systems, network switches. Serious analysis says that the Colossus consumes about 150 megawatts of full power. This is the consumption of the average American city. This is electricity for 150,000 residential buildings. And all this warmth does not go anywhere. It stays here, on Earth, in this building, and there is no way to put it anywhere. This is where real physics begins. Heat can be removed in 3 ways: through conduction, through convection, and through radiation. In data centers on Earth, convection is mainly used. The hot air has to move somewhere, cool it, and drive it through the equipment again. This requires huge chillers, pumps, heat exchangers, and colossal volumes of water. A Colossus-level data center consumes millions of liters of water per year. Literally millions. A local environmental organization has already sued the company because they started pumping water from local pipelines without getting full approval from the authorities. And this is only one object in one city. Now imagine what happens when there are 10 such objects. Or 100. The need for computing power to create true general-purpose artificial intelligence is not growing linearly. It is growing exponentially. Training systems of the AGI level costs, according to various estimates, hundreds of millions of dollars just for calculations. The next generations of models require several times more. Anthropic, OpenAI, Google DeepMind, Meta, and xAIs are already building larger clusters today. Forecasts say that by 2030, global electricity consumption by data centers alone will be equal to that of countries such as Germany or Japan. This is not an exaggeration. These are the calculations of the International Energy Agency, an organization that has no interest in instilling fear. The Earth simply cannot cope with what we demand of it. And this is where an idea comes into play that 5 years ago would have seemed like science fiction. Transfer computing to space. Move servers into orbit. To make AGI think over our heads in the literal sense of the word. Sounds crazy? Listen to what happens to physics when you do this. And then madness will begin to look like the only reasonable solution. There is no air in a vacuum. This is a banal fact that changes everything. Without air, convection is impossible. Hot air does not rise, because there is no air at all. This means that the only way to remove heat in an open space is radiation. Stefan-Boltzmann. Every body with a temperature above absolute zero radiates heat in the form of electromagnetic waves. And here's what is surprising. The background temperature in the open space is -270 degrees Celsius. This is almost absolute zero. This is the temperature of the CMB. Residual heat from the Big Bang. The temperature difference between the mountain server and the environment there is enormous. And the greater the temperature difference, the more efficient the radiation works. This is a direct consequence of the Stefan-Boltzmann law. The power of thermal radiation is proportional to the fourth power of temperature. Fourth, not the first, not the second. Fourth. This means that an orbital radiator with an area of several square meters can dissipate heat much more efficiently than a giant water cooling system on Earth. But wait. After all, there is the sun there. And the sun heats the surface of the satellites to plus 120 degrees Celsius on the illuminated side. This is true. That is why the architecture of the orbital data center must be thought out. The radiators are oriented perpendicular to the sun's rays, in the shade. And then they look directly into the open space, with its minus 270 degrees. And solar panels simultaneously look at the sun and collect energy. This is an elegant geometry that cannot be realized on the surface of the planet, where there is an atmosphere, clouds, day and night. Let's talk about energy separately, because this is the second key argument. Solar constant. This is the power of solar radiation per unit area, at a distance of 1 astronomical unit from the sun. It is equal to 1,361 watts per square meter. No atmosphere. No losses. On Earth, at best, about 1,000 watts per square meter reach the surface, and then only at solar noon near the equator. The atmosphere absorbs and disperses about a third. Clouds can reduce the incoming power by another 5 to 6 times. And at night, the solar panel does not work at all. In geostationary orbit, at an altitude of 36,000 kilometers, the solar panel receives a total solar constant almost continuously. Eclipses in the Earth's shadow occur only in certain periods of the year and last a few hours. The rest of the time, 24 hours a day, 365 days a year, a flawless flow of energy, no clouds, no fog, no winter. This changes the economy radically. A data center on Earth is powered by the power grid or by its own generators. The electricity grid means dependence on coal, gas, nuclear reactors, and all the complex infrastructure. Own generators mean fuel that needs to be brought. Solar panels on Earth operate on average 20 to 30% of the time, due to the night and clouds. In orbit, the same panels work almost 95% of the time. With an equal area, the orbital system produces 3 to 4 times more electricity. And when you consider that the efficiency of the panels there is also higher due to low temperatures and the absence of degradation from humidity, the advantage becomes even more pronounced. Now let's talk about what happens to the chips themselves. Semiconductors perform better at low temperatures. This is physics. Charge A carriers in silicon move more efficiently when there are fewer thermal fluctuations. The resistance of the conductors decreases. Current leakage through transistors is reduced. This means that the same chip at a temperature of minus 40 degrees works faster and consumes less energy than at plus 40. Not a little. Essentially. Experiments with liquid nitrogen cooling show an increase in overclocking performance from 20 to 40%. In orbit, the thermal environment is controllable. Point-wise, it is possible to keep the chips at an optimal operating temperature without the gigantic energy costs that accompany cooling on Earth. Musk doesn't just dream about it. It builds the infrastructure that makes this possible. Starship, the largest rocket in the history of mankind. The height is 90 meters. The thrust of the first stage is more than 7,500 tons. The payload capacity in a fully reusable configuration reaches 150 tons to low Earth orbit. For comparison, the Saturn V, the legendary lunar rocket, put 118 tons into low orbit. And Saturn V is disposable. Each launch cost several billion in terms of modern money. The Starship is designed to be fully reusable. Musk says the cost of the launch is ultimately about $2 to $3 million. This is 2 orders of magnitude cheaper than any existing alternatives. 2 orders. 100 times cheaper. This is what changes the equation for launching cargo into orbit radically. Today, it costs between $2,000 and $2,000 to put 1 kilogram of cargo into low orbit, even on the Falcon 9, the world's most fuel-efficient rocket. A server rack with equipment weighs several hundred kilograms. This is already hundreds of thousands of dollars just for the launch. At Starship's price of $2 million for 150 tons, the cost of a kilogram of cargo in orbit drops to about $13. $13 per kilogram. It changes everything. This makes the large-scale construction of orbital infrastructure economically meaningful for the first time in history. But let's talk about why AGI demands this scale. What is general-purpose artificial intelligence in general? It's not ChatGPT answering questions. It is not a facial recognition system. AGI is a system that is capable of solving arbitrary tasks at the human level or higher in any field of knowledge. Mathematics, biology, jurisprudence, engineering, creativity, strategic planning, all at the same time. Everything with a deep understanding. The best neural networks today contain hundreds of billions of parameters. GPT-4, according to unofficial data, contains about 1 trillion. The next generation models, those that claim to be at the level of AGI, will presumably require an order of magnitude more. This is more parameters. This is more computation and training. This is more memory. This is more bandwidth between the chips. Modern AI accelerators, such as NVIDIA's H100 or B200, are connected within the cluster by high-speed interconnections. NVLink. InfiniBand. The bandwidth between the chips inside the same server is huge. But between servers in different buildings, in different cities, it is radically lower. Delays are growing. This is a physical limitation. A signal cannot travel faster than the speed of light, and in an optical fiber it propagates about 20 to 30% slower than in a vacuum. Distances in ground infrastructure are the enemy of synchronization. The orbital cluster solves this problem in a different way. Satellites in low orbit communicate via laser interconnects in a vacuum. The signal travels at the speed of light, with no loss to the propagation medium. Starlink is already using laser inter-satellite communications. This is a real technology already working right now in Musk's orbital constellation. Let's look at the numbers. Starlink today has more than 6,000 satellites. Musk announced the second-generation Starlink with the number of devices up to 42,000. Theoretically, each of these devices can carry not only receiving and transmitting antenna equipment, but also computing modules. This is a distributed computing network right above the Earth's surface. There is no single building that can be destroyed. There is no single power source that can be disconnected. There is no one water supply that can be shut off. It is a decentralized computing brain on a planetary scale. And if the idea seems crazy to you, remember, the entire global internet seemed crazy 30 years ago, too. Let's talk about the specific physical constraints on Earth, because they are the ones that create the pressure that pushes the industry toward orbit. The law of MUR. Gordon Moore, in 1965, formulated the observation that the number of transistors on a chip doubles approximately every 2 years. This pattern has been held for half a century. But today we come to the physical limits. Transistors in the most advanced chips, such as those produced by the 2-nanometer TSMK process, contain gates that are several atomic lattices of silicon wide. Just a few atoms. There is nowhere to reduce further. Quantum fluctuations begin to disrupt the operation of such tiny structures. The leakage current is growing. Reliability decreases. Moore's law is slowing down. This is not an opinion. This is the consensus of physicists and engineers in the semiconductor industry. To continue to increase the total computing power, you need not to make chips smaller, but to make them larger in number. Build huge clusters. More clusters mean more heat. And more heat is again the same cooling problem we started with. This is a vicious circle from which there is no way out on Earth. The Earth's atmosphere is a warm blanket that does not allow heat to escape quickly enough. Oceans with water for cooling are a limited resource. The power grid is an infrastructure that needs to be built for years. Outside the atmosphere, there are none of these limitations. Imagine the Earth-Sun Lagrange point L2. This is a point 1.5 million kilometers from the Earth, in the direction opposite to the Sun. At this point, the gravitational forces of the Earth, the Sun, and the centrifugal force of orbital motion balance each other. An object placed at the L2 point remains there, in the Earth's shadow, protected from direct sunlight. This is where the James Webb Space Telescope operates. Because there is perfect darkness, perfect cold, perfect stability. The temperature in the shade at this point is close to -270 degrees. The radiators of the orbital data center at point L2 will work with the maximum possible efficiency. This is an ideal natural refrigeration unit. Free. Created by the physics of the universe. But orbiting systems do not have to be at the Lagrange point. A low orbit, from 200 to 2,000 kilometers, has its advantages. Less latency in communication with the Earth. It is easier to supply with the help of Starship. Easier maintenance in the future. In low orbit, the satellite circles the Earth in about 90 minutes. This means periodic passages through the Earth's shadow, but current battery or flywheel-based systems can smooth out these dips. Starlink has already solved this problem for communication satellites. For computational computers, the problem is similar. It is interesting to see how the space experience that already exists confirms these principles. The International Space Station has solar panels with a total area of about 2,500 square meters. They generate from 75 to 90 kilowatts of electricity. This is enough to ensure the life of the station, power supply for scientific equipment, life support systems, and all electronics. The ISS panels operate with high efficiency, despite the fact that technologically they are already outdated. They were developed in the 90s. Modern high-efficiency multi-junction solar panels reach an efficiency of 30–35%. Serial commercial panels for space are already producing 28 to 30%. On Earth, in laboratory conditions, the best results reach 47%. Progress continues, and the gap with ground panels in real-world conditions is huge. The ISS heat sinks are also already working. Ammonia cooling circuits divert heat from the equipment to radiators, which radiate it into an open space. This system has been operating for more than 25 years. Engineering principles have been worked out. The technology exists. The only question is the scale. And scaling is exactly what SpaceX and Starship can change the game in completely. Let's think about the military and geopolitical dimension. Orbital computing infrastructure is more difficult to physically control than ground-based infrastructure. Data centers on Earth are under the jurisdiction of specific states. They can be withdrawn, nationalize, disconnect by court decision, restrict access to the power grid, block access to water. Orbital systems are fundamentally more difficult to regulate. There is no international treaty that clearly defines jurisdiction over commercial computing infrastructure in orbit. This creates a completely new legal and political space. Not necessarily anarchic, but it is fundamentally different. Whoever forms this space first and launches the first orbital server clusters gains a huge strategic advantage. Musk understands this better than anyone. Starlink has already demonstrated military value in Ukraine. When ground communications fail, satellite communications continue to work. Similar logic applies to calculations. The AGI system operating in orbit does not depend on a single point of failure on the ground. It does not depend on the political decisions of individual governments. It does not depend on who controls a particular cable in the Atlantic Ocean. Now let's talk about the timeline. Where we are today, in the 2026 year, and where we will be tomorrow. Orbital servers with a practical AI computational load do not yet exist. But the work is already underway. Axiom Space is building a commercial module for the ISS and planning its own orbital station. D-Orbit, Exolaunch, Loft Orbital, these are companies that already provide services for placing payloads on satellites for commercial purposes. Lockheed Martin is experimenting with computing power on small satellites. Amazon, through Project Kuiper, is deploying a rival orbital constellation to Starlink. At the same time, chips are being developed specifically for space conditions, radiation-resistant processors, FSGA that can withstand space radiation, specialized AI accelerators with low power consumption. Radiation remains the main technological challenge. In low orbit, above the Van Allen radiation belts, the flux of charged particles is much higher than at the Earth's surface. Bit errors in memory and processors are more common. Semiconductors degrade faster. This is a solvable problem. There is a whole family of radiation-resistant electronics technologies developed for military and space applications. But they are more expensive and sometimes slower than commercial counterparts. Progress is needed here. And he goes. Companies like Samanova and Cerebras are developing AI chips with architectures that are fundamentally different from standard graphics cards. Some of these architectures are inherently more resilient to radiation failures. The next argument in favor of the orbital AGI is the delay in decision-making. An orbital system does not have to be isolated. It can work in close conjunction with ground infrastructure. Some of the tasks, heavy model training, large-scale parallel calculations, are performed in orbit. Tasks that require user interaction, responding to requests, and managing interfaces are performed on terrestrial servers with minimal latency. This is a hybrid architecture. The brain is in orbit. Interface on Earth. This is exactly how GPS, for example, works today. Calculations and reference time are generated by ground control centers, and the signal is transmitted via satellites. Hybridity is not a weakness. This is an elegant division of responsibility according to the physical capabilities of each component of the system. Let's talk about the Kardashev scale. Nikolai Kardashev, an astrophysicist, in 1964 proposed a scale for classifying civilizations according to energy consumption. A Type 1 civilization consumes all the energy available on its planet, about 10 to the 17th power of watts. A civilization of the second type consumes all the energy of its star, about 4 and 10 to the 26th power of watts. Humanity today is about 0 and 7 on this scale. We're not the same yet. In order to create an AGI and then a superintelligence that has nothing to limit, we need to go beyond the energy capabilities of one planet. This is not a metaphor. This is physics. The planet has a finite surface, final flux of solar radiation, finite reserves of water for cooling. A civilization that wants to create a mind that is orders of magnitude superior to humans must go beyond these limits. Orbit is the first step towards Kardashev's Type 2. Dyson sphere. A concept proposed by physicist Freeman Dyson in 1960. If you broke up the entire mass of Jupiter and created it into a thin shell around the Sun, capturing all of its light, a civilization would have access to the full power of the star. It sounds like science fiction. But the steps towards that, orbital solar panels, laser power transfer, massive orbital structures, this is engineering that we already understand in principles. Musk says that humanity must become an interplanetary species. This is not romance. This is an insurance policy against extinction. And at the same time, the only way to create an infrastructure powerful enough for a real AGI. Let's consider a specific example of what it could look like. Imagine an orbital platform at an altitude of 600 kilometers. Weight, 500 tons. That's 4 Starship launches in full cargo configuration. The platform carries 300 tons of solar panels. With an efficiency of 30% and a total solar constant, it generates about 40 megawatts of continuous electricity. The remaining 200 tons, computing equipment and radiators. With a consumption of 200 watts per teraflop, which is cutting edge for today's AI accelerators, 40 megawatts will provide 200 teraflops of computing power. This is not a giant cluster by today's standards. But it is a completely autonomous system, with no water, no ground power grid, no complex ground cooling infrastructure. Now multiply this platform by 10. For 100. For 1,000. With the cost of Starship launches decreasing by an order of magnitude, and with further progress in the miniaturization of AI accelerators, this becomes economically feasible by the end of the 1930s. There is one more important point that is rarely discussed. Earth's infrastructure is vulnerable to natural disasters. Hurricanes, earthquakes, floods, extreme heat, which just reduces the efficiency of cooling systems. Orbital systems are vulnerable to other things: geomagnetic storms, solar flares, collisions with debris. These are real risks. In the year 1859, the so-called Carrington event, the most powerful solar storm on record, would have knocked out modern electronics in orbit catastrophically. Protection against this requires shielding, duplication, and smart orbit design. But these problems can be solved. Military satellites are already working with radiation protection. The ISS has survived many geomagnetic storms. The technical risks are real, but they are within the engineering capabilities we already have. Let's discuss competition. Musk isn't the only one looking at orbit as the future of computing. Jeff Bezos and Blue Origin have long talked about moving heavy industry into space to keep the Earth clean. Blue Origin develops the New Glenn heavy rocket. Amazon is building Kuiper. Microsoft has invested in SpaceX. Google Cloud Computing is already serving AI workloads on a scale that requires new energy sources. All major tech companies are experiencing the same energy crisis. They all see that the Earth has limits. And all of them, each in their own way, look up. In this context, China deserves special attention. The China National Space Administration has announced ambitious plans to build an orbital solar power plant and transmit energy to Earth using microwave radiation. This is a different scenario. Not servers in orbit, but energy from orbit for servers on Earth. But the vector is the same, to use the orbit as an energy resource for calculations. In China, an experimental ground installation is already being built in Sichuan province to test wireless power transmission technology. This is not a fantasy. These are already funded engineering projects. Let's talk about neural networks and why AGI is the point where computing requirements become planetarily impossible. Modern transforming models scale according to the law. Doubling calculations during training gives a certain increase in quality. Researchers Anthropic, OpenAI, and DeepMind have shown that this scaling law, Chinchilla's law, continues to hold even at very large model sizes. There is no visible quality ceiling when simply adding calculations. This means that if there are enough calculations, the models continue to improve. But how much computation does it take for AGI to do so? No one knows for sure. Estimates differ by several orders of magnitude. The lower bound of reasonable estimates is about 10 to the 28th power of floating point operations for a one-time training of an AGI-level model. This is comparable to the total computing consumption of the entire global economy for several years. The Earth will not be able to cope with this with the current energy infrastructure. Mathematics says this unequivocally. Let's get back to Musk and what he's doing right now. XAY has expanded Colossus to 200,000 H100 graphics cards and announced plans for further scaling. It is the largest computing cluster for AI in human history at the time of its launch. Musk simultaneously builds Starship, develops Starlink, and directs Neuralink. These are not accidental coincidences. These are parts of the same plan. Neuralink is the interface between the human brain and AI. Starlink is a connection. Starship is going beyond the atmosphere. And the Colossus is the intellect itself. The four directions form a single ecosystem in which the orbital AGI is not a separate idea, but a natural next step. There is another aspect that usually remains in the shadows. Quantum computing. It is often said that quantum computers will solve the problem of computing power for AI. This is a misconception. Quantum computers are superior to classical computers in a very narrow class of problems: factorization of large numbers, simulation of quantum systems, optimization problems with a certain structure. Backpropagation training of neural networks does not belong to this class of tasks. They do not speed up the matrix operations that are the essence of Transformers' work and training. It's a different tool for other tasks. The energy problem of computing for AI is not solved by quantum computers. Another factor worth considering: heat emissions and climate. Data centers are already responsible for about 2% of global CO2 emissions. This is comparable to the aviation industry. With the exponential growth of AI loads, this figure will grow. Moving computing into orbit, powered by solar panels in a vacuum, isn't just a solution to the cooling problem. This is a radical reduction in the carbon footprint of AI. The heat that the servers radiate there escapes into interstellar space. It does not heat the Earth's atmosphere. This is physically impossible on a noticeable scale. The distance to the nearest stars is such that any thermal radiation from orbit is completely scattered in space. The climate arguments in favor of orbital computing are very real. Let's consider the engineering details of an orbital data center. Each component must withstand startup, vibrations, overloads, vacuum, radiation, thermal cycling, that is, alternating extreme heating and cooling when passing through the shadow. It's not just about putting a server in a rocket. A complete redesign of the design is needed. Boards should work without humidity, without ventilation. Connectors must operate under vacuum conditions. Heat must be dissipated through the thermal interface plates to the radiators, not through the air. All this has already been done for military and scientific satellites. But commercial scalability costs money. It is the cheapening of Starship that changes the equation. When shipping becomes cheaper, you can afford to make components heavier and more secure. Less need for extreme miniaturization for weight loss. Another technological element: controlling the orientation of satellites. A large orbital platform with large solar panels and radiators must constantly adjust its orientation. Panels on the sun, radiators in the shade. This is a challenge for gyroscopes, thrusters, and attitude control systems. SpaceX has tremendous experience in controlling the orientation of Starlink satellites. This is already a proven technology on the scale of thousands of devices. Let's talk about the next level. What will happen after the orbit? If AGI is created, and if its computational requirements continue to grow, the Earth's orbit also has limits. The solar flux of 1 square meter in the Earth's orbit is enough for 1,361 watts. Multiply by the area of a circle with a radius equal to the Earth-Sun distance. This is the total power of solar radiation intersected in the Earth's orbit. It is huge, but still finite. The theoretical limit of calculations limited by the power of the Sun and located in the Earth's orbit is a few hundred zettaflops. That's a lot more than AGI needs. Enough for reason the scale that we cannot imagine today. But the fundamental logic is the same. Going beyond the Earth's surface opens up access to energy several orders of magnitude greater than the Earth's. And now we return to where we started. Colossus in Memphis. 100,000 graphics cards. 70 megawatts of heat. Whole rivers of water for cooling. This is not the final answer. This is a transitional stage. Terrestrial supercomputers are something we can build today, right now, from available components. Orbital computing clusters are what we'll be building tomorrow when Starship makes launches cheap enough. An AGI who can change civilization is something that can require both at the same time. Musk says that AGI will appear sooner than many people think. Perhaps by the end of this decade. Sam Altman of OpenAI agrees. Demis Hassabis of Google DeepMind is more cautious, but also does not say that it is several decades. They all see the same thing: the curve of growth in computing capabilities and the curve of growth in the quality of AI models converge at a point that is not far away. It's not the point of AGI being created. The bottom line is whether we will have enough energy and cooling to run it. And the answer that Musk is building right now with metal and rocket fuel and solar panels, this answer sounds from orbit. Physics chose for us. Our planet is too warm, too small, too dependent on the atmosphere, day, night, clouds, and water. There, beyond the atmosphere, there is cold and emptiness, and the sun never sets below the horizon, because there is no horizon. The AGI of the future, the mind that will change everything, it will think over our heads. Literally. Soaring in zero gravity, covered by the shadow of the planet, under the eternal light of the star. Musk looks up as everyone else looks at the server racks. Orbit is not romance. It is an engineering response to a physical problem. And physics, as always, is right.